Frequency domain analysis of series RLC circuit for underdamped system, critical damped system, and overdamped system. Okay, by taking the values of inductance, L is equal to 8 millihenry, C is equal to 2 microfarads. By fixing this inductance 8 millihenry, C is equal to 2 microfarads. So by changing the values of resistance 1 ohm, that is called underdamped system. If resistance is equal to 4 ohm, that is called critical damped system, and the resistance is equal to 6 ohm, over damped system. So for this system, so we have to identify the how frequency domain analysis, phase plot and magnitude plot changes. Okay, by changing the values of resistance, that means underdamped to critical damped to overdamped. For three cases, we have to understand the how frequency domain analysis changes: gain margin, phase margin, and omega BC, omega GC, and also how gain phase plot changes, and also how magnitude plot changes. We have to understand by using Bode plot. Okay, by using PSpice also. So in this schematic, first we have to take for underdamped system, there is 1 ohm resistor. Okay, and here AC magnitude is called 20 volts. So any type of voltage range 20 volts, 20 volts. Okay, V naught of S by VA of S. That's why the magnitude is independent of the output. That is called our output across the capacitor. That is called frequency domain analysis. Okay, is nothing but a transfer function. By using transfer function, we have to find phase plot and magnitude plot. So in this expression, in this experiment, by changing the values of inductances to 8 millihenry and capacitance to 2 microfarads, and resistance is called 1 ohm. So this is for underdamped system. Okay. So here this is called phase plot and VDB is called magnitude plot. The orange color is called VDB, that is called a magnitude plot, and VP is called phase plot across the capacitor. Okay, and analysis is called analysis setup, and here ACCP analysis and decade. Okay, and starting frequency 10 and ending frequency is called 10,000 kilohertz. Okay, so in this way we have to give the analysis setup. After the analysis setup, simulate. Okay, simulate, and then the graph will be displayed in this way. Okay, so to separate these two waveforms, phase plot and magnitude plot. Okay, in this schematic diagram, VDB decibels plot, that is called orange color. This orange one is called orange color plot is called dB plot, magnitude plot, and this green color is called phase plot. Okay, to separate this two plots, the same x-axis, but to separate on y-axis, press this Control X. Okay, and go to plots, add y-axis. Okay, then Control V. So like this, two waveforms are separated on same x-axis, and y-axis is different here. So y-axis is different for phase plot and magnitude plot, but x-axis is same, frequency. Okay, so this is our 0 dB line. 0 dB line. This is called this second one is called dB plot. Okay, this is called orange color is called dB plot. That is nothing but magnitude plot. So in this magnitude plot, for corresponding 0 dB line is called gain crossover frequency. So by finding like this, so this is called 0 dB line. This is called 0 dB line. So corresponding 0 dB line, where it is touch this line is called gain crossover frequency, 0 dB line. And then when we are extending in downwards direction, this frequency is known as gain crossover frequency, 0 dB line. When crossing this point, 0 dB line crossing point is called gain crossover frequency. So here this is called grain crossover frequency. Fine. And similarly, this is called phase plot. In this phase plot, okay, in this plate plot, so minus 180 degrees line. So it is up to minus 100, and then so select this phase plot, enable toggle cursor, and press here. Okay, minus 179 point minus place plot display like this 179.99. Okay, for 1100 kilohertz, for 1 megahertz, it is come minus 179.99. So very high frequency we are getting at omega is equal to minus 180 degrees. So for minus 180 degrees, okay, the frequency is nothing but above 1 megahertz. So very high value of frequency we are getting for minus 180 degrees line. Okay. So when it is crossing the minus 180 degrees line, that the line is called phase crossover frequency. Here phase crossover frequency is approximately so 3.73 megahertz. Okay. And then next for changing the values of resistance to another values, you will get critical damper system. Okay. Critical damper system. For critical damper system, what is the value of resistance? R is equal to 4 ohms. So in the schematic, change resistance R is equal to value of resistance R is equal to 4. And save, and okay, simulate, and then so this is our magnitude plot for critical damper system. This is our phase plot, critical damper systems. Okay, so if you want to separate, select this and VDB and press Ctrl X and go to plot, add y-axis, Control V. Okay, like this, y-axis is separated, x-axis no changes. So this is about magnitude and phase plot for critical damper system. A 0 dB line, okay, and this is called our phase plot. Magnitude line, magnitude plot. This is called magnitude plot, and this is called phase plot. Okay, understood. And then similarly, so we have to find for overdamped system, by changing the resistance R is equal to 6 ohms, then you will get overdamped resistance. Then for overdamped resistance, so we have to take the values of inductance. Resistance is called 6 ohm. Then simulate. So in this way, the waveform is magnitude plot is changes like this. The magnitude plot and phase plot by separating this Control X plot axis. So not axis setting. Go to plot, add axis, Control V. So like this, the plot is changed, I mean separated y-axis and x-axis. Y-axis. This is called magnitude plot. Phase plot is changes. For overdamped system, in this way we have to execute. And if you are increasing the values of resistance 6 ohm to, for example, 10 ohm, then how phase plot and magnitude plot changes we can observe in this. Okay. The phase plot is changes this way. So the phase plot is called phase plot. This is called magnitude plot is changing like this. And then similarly, so I'm changing the inductance to very high value. So value 10 to 100 ohms. If it is 100 ohms, and then how phase plot and magnitude plot changes like this way. Okay. So by changing the values of resistance, this is called overdamped system. And press Ctrl X and go to plot, add axis, Control V, and change the width of the plot. So in this way, this Bode plot and this Bode plot, magnitude and phase plot is changes. Okay, so according to our system. Oh, okay, for critical damped system, so for resistance is, if it is resistance is equal to 1, critical damped system simulate. So like this, the magnitude plot and phase plot. This is called magnitude plot for critical damped system, and also this is called phase plot for critical damped system. Changes in this way. Then here, if you are increasing the resistance value of resistance, so 100, then what happened means here simulate, and then so the waveform is changes like this, Bode plot and magnitude plot. Okay, this is called phase plot, changes according to our system values, RLC values. By changing the values of RLC, that means critical damper to over damper system. When the changes, the phase plot is also changes in this way. Okay, this is about frequency domain analysis of series RL circuit for under damper, over damper, critical damper systems.